So we look at these people and we think, well, these are people working and working hard, perhaps. And there is no question about that. Nevertheless, it doesn't mean that what they're doing is value. What is value? Do you still remember that? Value is what the customer pays for. And I can bet you, customers are not paying for these kind of meetings. They just pay for a result, an outcome. In real life, most of what people do, whereas that is an office or a factory, consists of non-value activities or waste. The Japanese have a special word for that. It's called muda. So today we're going to explore that, what we like to call lean thinking. The goals that you will learn are, number one, the distinction between value and non-value activities from the lean perspective. The second goal is how to analyze and improve a process by means of a tool which is called the value stream mapping. I have the feeling that you have heard that technique before. I don't know, it's just a feeling. Alright, so you might remember this. Once upon a time you would go to McDonald's and you would select your hamburger and fries of your choice. You would order that to the person waiting there and he will retrieve that item, straight from this shelf. Now, this shelf contains a lot of products which we can say this is inventory waiting to be consumed. And you know what happens to inventory waiting to be consumed? Sometimes it doesn't get consumed. So it becomes literally waste. They have to throw these hamburgers to the trash because, hey, who's going to buy that? Who's going to buy an old hamburger? So no one. So every day McDonald's did that, just like the rest of the fast food chain restaurants. But McDonald's changed that. Now, this picture might look familiar to you and very natural because if you have been to McDonald's, the very first step that you do is you go to that screen. It's very attractive. I would recommend not to touch it directly, especially nowadays with the coronavirus, who knows. But step number one is to go there and order. You would order, you will assemble an order, pay it, and the employees will receive that order and then they will start to assemble that order, to manufacture that order right on the spot. Eventually, another employee will bring that order with a big smile to your table. That's kind of the new cycle. This cycle is nothing new. It actually comes from the auto industry. That is the so-called just-in-time system. The hamburger gets produced in the moment it gets ordered, not before. So, just-in-time is a method where material arrives or gets produced just in the time when it's needed. It is actually the Toyota production system that some people refer as TPS. But the Americans, and more specifically engineers from the MIT, they like to call it lean. Lean as the opposite of fat. Yeah? Because fat is bureaucracy. Fat are complex procedures that takes a lot of time and resources. Lean is very focused. So lean is about improving flow and speed and at the same time reducing complexity and waste. Or muda, once again. Lean is a combination of problem-solving methods and tools now popular beyond manufacturing. So now you see lean applied to restaurants, hospitals, offices, theaters, etc. This is an interesting chart that I found on a tool called Google Ngram. And what it shows you is the occurrence of just-in-time in literature over time, according to that tool. So you can see that in the 50s, it was like nobody was really talking about it. And then suddenly, right from the 80s, boom, you have this ramp up. That is actually the time when these MIT engineers went to Japan. So they discovered what they were doing. Japan economy was growing like crazy, and everybody was wondering what is their secret. I remember myself, I was still a young guy back in the 80s. I still remember seeing books about that maybe the Japanese language was the secret, because who knows, maybe they think in a different way. So it was nothing like that. It was just a method. And it was a method that was built through time, becoming better and better. Nowadays, of course, you can also see that it's kind of fading out, but it doesn't mean that it's not applicable anymore. It means that it became very common, almost like common sense. This is how we always do things. So that is the reason that explains this slowdown in, let's say, in reference or occurrence. Okay, so look at this place. What do you think it is? Is that a hospital? Well, it looks even cleaner than a hospital, or even some universities that I know. This is a lean environment. This is a factory, and believe me, it is so clean. You can actually put some food here on the floor and eat it straight on. You can do the same everywhere, because that place is always maintained. Every single table has an owner. Do you know who the owner is? That worker who operates there. He has ownership. This is a lean environment. Lean environments also happen in offices, as we can see here. You notice here is a desk, and look at these tools. They are properly arranged, just like these ones. This is a drawer, and everything is in its right place. Here you have even some descriptions. Sorry, I don't read Japanese. You have to forgive me, but I can imagine here it reads scissors. It looks like that. And here it reads calculator. So why is, and look here, this is also interesting. The system is already telling me that something is missing. What is missing? Oh, whatever is written here, which I have no clue. But the system communicates with the person who is using these tools. You see, it's very logic and very good. You don't have to deal with the mess of not finding your tools or having an excess of items that is just makes your working place horrible. So Lean provides a lot of advantages in terms of how you work. So the perspective of Lean is that every job can be analyzed from three views. One is value activities, non-value activities, which are pure waste and they have to be eliminated right away, or non-value required. Let's have a closer look. Value is what the customer is willing to pay for. Customers are not paying for meetings. Customers are not paying for inventories. They are not paying also for moving goods inside of a warehouse. Customers pay for a specific product or service, which is always good and not defect. This is what they pay for. Non-value is a list of items such as waiting. An item that is waiting to be processed because who knows, maybe that equipment that is going to do that job is not ready or is broken. Waiting is also when you go to a store and you have to wait in the line. That is waiting. Actually, the line is inventory. Pure waste can also be rework. Sometimes in factories you don't do something right and then you have to repair it. But it also happens in offices. Maybe it had happened to you as a student as well. I mean, how many times have you done a paper, a report, and then it was not okay, and then you have to redo it? So that is waste. Sorry, you have to eliminate that habit. Now, non-value but require are, think about administrative activities which are triggered by policies. It's more like, hey, we don't like to do it, customer is not paying for it, but we have to, because that's how the procedure stipulates. Maybe we have a certification that tell us, hey, you have to inspect your product at the end of the line, okay? Removing parts from a pallet, cleaning tools. I think it's important to clean a tool. Picture going to the dentist and the dentist is not cleaning the tools that he's putting in your mouth. Hey, come on, of course they have to clean it, but you're not going to pay more just based on the number of times this dentist is cleaning these tools. You just expect that they are clean, or let's say you expect that you get your teeth fixed and that you leave that office at the dentist without any kind of infection because the tools were not clean. Inspecting is also a type of waste because the customer doesn't pay for inspection. They pay for a good product. But sometimes inspection has to be performed in order to control or to ensure that indeed that product is good. Okay? So it turns out that with regards to waste, we have actually 7 types. We can categorize waste in 7 different forms. Let's just call them the 7 types of muda. Okay, so the very first waste that I'm having here to present you is movement. Movement, motion, unnecessary movement of people within a process. Picture a worker that in order to assemble a part, he needs to go to point A and point B and in order to bring some materials and then he can work. Picture maybe in an office, people walking around all over the place. This is motion, excess of motion. This is a form of waste. Waiting is another form of waste. It can be people, like when you go to the dentist at the time of your appointment and yet you have to wait. This is a form of waste. Or it can also be parts waiting to be processed. You have inventory, as we have discussed, because inventory is pure money. It's money waiting there. So that can be raw material, that can be finished goods. It can also be work in progress. You still remember that? Overproduction, that means producing more than is needed, just like McDonald's. Maybe having too many Big Macs there that at the end of the day nobody wants to buy. So that is something you want to eliminate, you want to identify. But you also want to avoid overprocessing. What is overprocessing? Well, if we use the example of the Big Mac, imagine making such a beautiful Big Mac, so perfect, arranging the tomatoes in a very beautiful way. And at the end, that hamburger ends up in my hands. And I don't really care how the tomato is arranged. I just want to eat it and I just expect that the hamburger tastes good. It's warm, smells good also. So I don't care about that. So that is overprocessing. This shouldn't be done. It's kind of a cost of quality, so to say. We have transportation, which is similar to movement, except that in this case we are moving goods. Picture inside of a warehouse, a forklift, which is moving pallets back and forth. Hey, sometimes you cannot avoid that, but you want to minimize that transportation, right? You want to arrange your items inside that warehouse so that you minimize the transportation. And lastly, defects. I think I don't need to explain you that. Not right at first time. Sometimes it happens. That is something to be avoided. Okay, so this lean thinking can be applied to all sort of activities or jobs around us, and that is not only manufacturing. That could also be a hospital, because just like in this case, you have a part that is moving here. Well, it's not really a part, it's more like a body, but this person is also moving. Look, it's even on top of a table with wheels. And just like here you have operators, here you also have operators. Of course, these are more sophisticated people in terms of education, but they are performing a similar type of job. But the same could also happen in services, like in an office or a hairdresser, in which the customer is also flowing and someone else is performing a job. Maybe we have a look at how this can be applied. Okay, so let's measure what we call the process cycle efficiency at a hair salon. And we are going to create a flowchart, and we are going to analyze every single activity that is happening there by means of these 3 categories: total value, time, non-value added, and non-value added but required. Okay, so here it goes. You arrive to that hair salon, and it turns out that you have to wait, sitting on a sofa, reading magazines together with other customers. Eventually, they call you up, hey, please come and sit now in front of this mirror. Now you can sit here, we're getting ready. Okay, so you go there, and then you have to wait again. It happens all the time. You wait there because the hairdresser might not be ready to work, and he needs to bring, his tools or her tools, and sometimes are not available, or they don't have battery in the case of a trimmer, for example. So you're just waiting. Sometimes they even give you a coffee for that. They wash your hair before cutting. They ask you, hey, what is it that you need? How do you want to have your hair? And sometimes that is a very straightforward explanation. Sometimes, in some cases, it lasts longer because either the customer cannot articulate the need, or the other person cannot understand, or both at the same time. And eventually you get the haircut. There is an inspection because, hey, maybe the person didn't cut it right, or the color applied to that hair was not the right tone. So there is this checking of results. And then, if that is applicable, there is a rework because, hey, the hairdresser didn't cut it right, not short enough. Okay, so eventually there is the invoicing and payment. Okay, so let us apply these categories. We can say that waiting, that is pure waste, right? You don't go there just to sit on a sofa. Motion is waste as well. Waiting, waste. Any form of waiting is waste. But washing is something that can be considered waste because you also don't go to a hairdresser to get your hair washed. That's kind of weird. But very often it is required. So let's just color that with yellow. Needs appraisal is kind of an administrative kind of thing, so we can also call it yellow. But the cutting of the hair is definitely green, because the reason why you go to a hair salon is for what? For that purpose, that's right. Then you get an inspection, rework, and invoicing and payment, which is an administrative task you cannot eliminate because you have to pay. So imagine that you go there with a clock and then you start timing. And maybe this represents in minutes the time in which every single activity is being performed. So 5 minutes washing, 5 minutes needs appraisal, 15 minutes for the haircut, inspection, rework, and invoicing and payment, just 1 minute. Okay? Now you notice something here already, that all the data, all the timings are arranged here except for this one. So the next step is to add all the non-value activities, which are the ones that we see here on the top. We also do the same for the value activities. And you can already see the big difference between both. And these are key figures for calculating the process cycle efficiency, because the way to calculate that is by dividing the value time to the total time. And the total time means the complete lead time needed for a customer to flow in this system. That is the cycle. So 15 divided by 64 will lead us to 23%. So we can say that on average, what is being done to a customer, only 23% can be considered value. The rest is non-value added. Then the next question perhaps will be, how can we improve that? And then it will be about optimizing some of these steps, or perhaps completely eliminating. And there are all sort of creative solutions to do that. We don't want to have people waiting in front of a mirror while the hairdresser is looking for hair or his tools, right? So the same logic applies to other manufacturing environments, like the one that we see here, in which the inputs or raw materials are being transformed. They are being moved here and there, waiting to be manufactured, and finally they get processed, and it's only 5%. The rest of the time is just waste. And that's a lot of money and that's a lot of effort. It has to be recognized and it has to be seen like that so it can be improved, it can be optimized. So we can identify, remove or reduce waste by analyzing a process stream. That is the stream because items are flowing just like in a river stream. And the method is called value stream mapping. Okay, so value stream mapping is what you see here. It's a data-rich visual representation of process regarding information, material, and time flow. So you get a big helicopter view from the whole company on how they produce their main, or let's say their core process. Because at the end of the day, you might remember from Porter, we have support and primary activities. This is the primary activity. So value stream map is actually a method for improvement. So it's a bit more than just mapping a process. In fact, it's a process in which the current state gets assembled, just like in this picture. You see, these are actually the workers involved in the process, because who else is the expert in that but the person that actually does it? And then it's about redesigning the process, and that's what we call the future state. And that is the reason why maybe here in this example they use post-its, because they reallocate, they eliminate steps, and eventually once that gets drawn, it gets implemented. So you need a deployment strategy for that. Okay, so the value stream map uses a lot of symbols like the ones you get to see here, sometimes trucks, even planes, arrows. They have some particularities because you have arrows that express movement of materials, but you also have arrows that express information flows, even as hard copies like orders or even electronically. You also indicate the number of operators that a specific workstation might need. Here, you remember that? That's the inventory triangle. It is also used here. Okay, so just having a closer look at the type of data that we can have at the data box. We might have takt time, which is daily availability and by daily demand. So that is the rate or the heartbeat of the production floor based on what is demanded and based on what is available. You have cycle times, you have setup times, or also known as changeovers. So here be careful because sometimes you have ST or CO. That is the reason why. We can calculate per unit processing time, because if we already know the cycle time for a particular workstation, and we also know the setup time as to produce a batch, a collective number of units, we can calculate the equivalent per unit at the cycle time to it, and then we can get the complete processing time per unit as how long it will take a unit to be processed. We can also calculate what it is also referred as the total lead time, which is the total processing times, which is value, by the way, plus the total inventory times, which is non-value, but the units, they flow through it. There is, as a small remark, sometimes you have more detailed information like up times or down times, and these are basically percentages expressing how intensive that equipment has been used. Alright, so let's make this exercise. Jensen Bearings makes two types of retainers, S and L, which follow the same process steps. That means they belong to the same product family. That means we can use the same value stream map for both products. Both products are packaged and shipped in returnable trays with 40 retainers in each tray. Those 40 retainers, these are the amount or the quantity of units per batch. This is an information that will be useful later on. So the questions are: A. Create a value stream map for Jensen Bearings. B. What is the takt time? C. What is the total process lead time? D. What is the system capacity? Or in other words, how many units per day can we produce? So let us start. This is our data. These are the overall these are the attributes that we have, in which we have an average demand of 3,200 units per week, batch size 40, number of shifts per day 1, in which people work 8 hours, but they have 2 30-minute lunch breaks. What does that really mean? It means they only work effectively 7 hours a day. Every step that we have 4. This is what is happening: pressing, pierce and form, finish grinding, and shipping. It has its respective cycle time, setup time, uptime, number of operators, and stock or WIP. Sometimes that stock is expressed as days. I will clarify that later on, how to calculate that. Sometimes that is expressed as units, and we will need to translate that into time. So we have all this data, and we also have additional data about customer shipments and also information flow. It turns out that all communications from customer are electronic, and this information concerns forecasts which are sent every certain number of days, daily orders. We also know that all communications to suppliers are electronic. Same story as before: forecast, weekly fax. I hope you know what that is. This information is relevant for the construction of the value stream map. There is a weekly schedule manually delivered to press, pierce, and form and finish grind. So these are like in the shop floor, these are areas in which the production control is sending orders indicating what needs to be produced and when. And these orders are sent manually. Once again, this is relevant information for building the value stream map. Okay, so let us start with the first question. Create a value stream map for Jensen bearings. My recommendation is to always start with the material flow, then to continue with the time flow, and eventually the information flow. So when doing that, you should be able to construct something that resembles this. Now, of course, this picture looks very professional and beautiful. In real life, people just draw it, and it is a bit more messy. Sometimes they use post-its, as you might remember from the previous slides. But this is just to have a clean-cut visualization. We have here our process, where parts are flowing. These arrows represent the movement of parts. These triangles in between represent WIP, indicating the number of units that we have in between. Now, something very important here is, please remember, when looking at this data, it is not as if this number of units became this number of units. No, it's nothing like that. It's more like a snapshot, a picture of what was going on at a certain moment. It is as if you just go to the production floor and then record on a piece of paper how many units do they have in between these two equipments, how many units do they have in between these two workstations, and so on. You might also collect some cycle times, and of course everything is on average. What you might not have right away is this. So you notice now we have here the number of days that these units represent. There's a very easy way to calculate that, and I will show you that in the following slides. Moreover, on top we have the information flow. You see the electronic information flows of daily orders and forecasts reaching to production control department. That is a department inside your factory. These are the ones sending orders to the shop floor of what needs to be produced. And once again, we also have communication with our supplier. So, supplier area, sending raw materials, customer area in which we ship our finished goods. And that's the cycle. Okay, so what is the takt time? Takt time is basically the calculation of daily availability and daily demand. So let's do it. So daily demand, we learned that we have 1,000 plus 2,200 pieces. Remember here, these are the L and the S shape. Yes, it's okay to add them up, although they have a different shape, because we treat them as equal, because they just follow the same process steps. We divide it the number of days in which we are operating during a week, and we have our daily demand expressed as 640 pieces a day. This is what is demanded. The time that we have available for producing those pieces per day is 7 hours a day. Remember, we deducted that hour from the 8 hours a day, and then we just translate hours into seconds by this simple calculation, and then we obtain 25,200 seconds a day. So if we run the math, we're going to end up with a takt time of 39.37 seconds a piece. That means if we produce at a production rate of 40 seconds a piece, we won't meet our demand. So that is really the limit. As long as we produce that or a bit less is fine. If we produce way faster, let's say 30 seconds a piece, that could create another problem. Which one? Well, maybe you already know. Stock. We might be building more than it is needed, and that is also a form of waste. So what we want to do is we want to approximate the takt time as much as we can. So we have a current system operating. So what is a complete process lead time? Okay, so that means how long it takes for a unit of raw material to flow through the system, as if that would be a pipeline in which it stops by the WIP inventory, so that could be days, and then it gets transformed and then waits and so on. So we need to calculate the total lead time. So we're going to start first with inventory time. And here is something interesting. We can translate number of units into time by the following formula in reference with the daily demand, as if every day I'm selling, 200 hamburgers, and I am having 400 pieces of meat for the hamburger. So that means that we have 2 days of inventory, right? Okay, so here is the same logic. The WIP between press and pierce and form is calculated as 2,250. That is the sum of units that we have there on top of a pallet, divided by 640. What is 640? Well, that is the daily demand. Remember, we just calculated that? When doing that, we obtain 3.5 days of inventory. This is how we should see that stock. Just in case you don't remember, these are the units that we just add them up. And here goes to the time ladder, the 3.5 days. So we are always translating these units into time so that we can construct our time ladder, which, by the way, that was the missing element on your project of PMA 8. Okay, that was just a hint. We continue with the following calculations, just like before. We calculate, and eventually raw material is already expressed as days. So we can say that the total inventory time is 16 days. This is what it takes, just waiting for a single part. Now, what the amount of time for that part to be completely processed, which is what the customer actually pays for, which means that's value, is the following calculation. It's the sum of the cycle times. You see that number? It looks very small, right? That's right. So that shows you already the proportion of value and non-value added activities. So we have to do something about this, definitely. Okay, so what is the total lead time? 16 days. Now, you may argue, well, it's not 16 days 0.0, it's more like 16 days 0.0003 because of the seconds. But hey, it doesn't matter anymore. The difference is so abysmal that we just rounded up with 16 days, just to make it even worse. So that is our total lead time, highly defined by total inventory time. Okay, so we have the next question. What is the system's capacity? Where capacity can be defined as the maximum amount of output that can be obtained through a certain machine or production line. We're going to find out by means of identifying the bottleneck, which is the slowest workstation, because that is what defines the capacity of the complete system. So we have our 3 equipments, and we have our cycle times and setup times. So what we need to do is to calculate per unit processing time, which is of course the cycle time, but also the allocated setup time per unit. And we have already this time given, it was given to us like 10 minutes, but we need to allocate that as per unit. So that means dividing that by the number of units that we have in the batch. So 40 units in this case. So if we translate, and if we run this calculation by translated minutes into seconds and divided by the number of units, we obtain 15 seconds. So 12 plus 15, that's 27 seconds. And the same occurs for the rest. Now, here's a question to you guys. Which from these three workstation represents the lowest or the bottleneck of the whole system? Is it this one? Of course not. That is the fastest. It's actually this one here. Okay, so it doesn't matter how fast you can run. At the end, everybody runs based on the bottleneck. That is what defines the total speed. And because of that, we are going to calculate this maximum amount of output based on what we can do or what we can produce. So we do it like this. So if a day has 25,200 seconds, that's really a lot, and we produce units every 38.5 seconds, then we can say that we can produce 654 units a day. You saw how easy it was calculated? Now maybe an interesting question would be, do we have enough capacity to fulfill our demand? Can we produce what is demanded? So let's have a closer look. Let's compare what is needed versus what we can do. What we need is to produce at a rate of 39.3 seconds apiece. What we can do is to produce at a rate of 38.5 seconds apiece. That means that we are still faster than what is required. That means by producing at this rate, we are capable to produce 654 units a day or 3,270 units a week. But wait a second, do we need to produce them all? No, we only need to produce 3,200 pieces a week because we are working on a just-in-time system. So we produce what is needed when it's needed. So at this moment, even though we have a lot of inefficiencies in the system, we can still say, yes, the system can fulfill the demand. I hope that you got how the value of the value stream map is a very powerful tool. In fact, there is a hospital across the street from Fontis, and one day I was just walking by and I saw this poster, and it's a poster of a project. It seems to me that it's about the reduction of diagnosis or something. So that is the process. And here you have a report that expresses the current situation, the as is, and the new situation. So you can already see how it was very long and complex, and it became very lean. You have further details of conclusions and how much money they save and all that. Now, what do you think is flowing in a hospital? That's right, patients, people. So this is what is being measured. So just like parks, we measure patients as how long it takes for a patient to flow in the system. And then we can also identify value-added activities and non-value activities. They also have inventory. It's just that the inventory is just people. So that shows you how lean thinking is applied in hospitals and how in particular value stream map has been applied just in the hospital across the street. This is just to show you how useful this tool is. I hope that you enjoy this lesson and that it clarifies some of your questions. Thank you very much, and bye-bye.